All right, thank you. It's true, I cheated. I'm a researcher here at the Institute of Computer Science, and I did not know it was a competition, so now the stakes are high.
No pressure.
No pressure, and you can see the title has changed a bit from the schedule because we had to resubmit the article while the slides were already sent. So the new journal just had a limit on the title length, so it did a different wording. So it's a very kind of theoretical, kind of commentary piece, but it's also on a very practical topic and a very specific topic, but I will get into it. And we wrote it with my colleagues, and we'll see if it gets published as well. But the background is that for those of you who do not know, in this September, the Estonian education system will have an AI leap, which means that the gymnasium level students will get access to some sort of AI tool, educational AI tool. We do not know what it is exactly, but it will be there, and we will somehow use it to be more effective in learning and teaching. And as me and my co-authors were looking into this, we had a déjà vu moment, like, hey, we have seen something very similar like this, like about a decade ago. And this was from the huge hype surrounding the virtual reality revolution that would also change education as we know it. So back then, in 2015-16, I was very much riding that hype wave and was deep into these topics. And now 10 years later, I can tell you the VR revolution really never happened. There are many problems around the technology and how to apply it. And in this article, we try to see if these lessons that were there in the VR revolution, can some of these be applied to the AI revolution? Or will we make the same mistakes? And the outcome will be the same as well. The overview is that we had three main issues that we wanted to kind of unpack in the article. One was that, well, both VR and generative AI have kind of like questionable benefit in this broad secondary education, at least. And also, the user studies that have been done so far, both in VR and in generative AI, they have quite poor methodology when you look at the actual experiments being done. So even if you do find benefits, are these benefits real? And thirdly, we see that these financial costs, both for VR and Gen AI, they might be severely underestimated. Currently, we're riding on the hype train, but when reality hits, it might be a bit more complex story. But I will get into these in these remaining minutes. But a bit of background, like to set the scene. Obviously, the educational system is no stranger to revolutions, would-be revolutions. These are called teaching machines, ways that we can somehow either replace or augment the teachers in the classrooms. So at first it was the radio, the television, CD discs, and so on, that promised to make the classroom totally different. But still, when we look at the classroom today, it's quite similar to what it was 100 years ago. There are some, touchscreens here and there, but the fundamentals have been quite the same. And when we look at these technological edtech solutions, these products, they are mostly not informed by pedagogical science, but more like trial and error kind of artisan approaches, like, okay, we have this technology, can we somehow use it in education? Can we somehow find a problem that we can solve with this new fancy technology? And when we talk about VR, at least in this article, we mean this very high-end VR that you wear a headset, you are like transported into a different virtual reality environment. So it has these displays, it has the body tracking, and it has stereoscopic vision, so you actually can perceive depth and so on. And with Gen AI, we kind of distinguish from other AI applications. One good kind of example is this sentence that these Gen AI applications are substantially broader and more intellectual compared to prior examples of AI, and they are highly unreliable and often provide incorrect responses, which is still true today. And why we have this narrow focus is that, well, in Estonia, the AI leap will happen first in this 11th and 12th grade. No, 10th and 11th grade. Which means the students are 18, 17 years old. And we also look at the larger secondary education field, which is like ages 13 to 18. So the problems that I outline here, they will not probably apply to university students, to doctoral students who have this high level of critical thinking already developed, hopefully. And I have also bolded out this broad rollout. So yes, you can have a small group using AI, but what about like a large mass rollout of these technologies? In Estonia, we're talking about 20,000 students. How would that work on a practical level? So just going over these points, it will be a wall of text, sorry, but I will try to, I don't know, put some jokes here and there. So, benefit in education, which should be like the first and foremost of any technology. When we introduce it into the classroom, is it beneficial? And when we look at VR, there have been studies saying that yes, you can train people faster, you could have more focus while they're in the headset, a higher emotional connection with whatever they're studying, but at the same time, they have higher cognitive load that they need to deal with, because now you're kind of in two realities. You're in the real classroom, but also in this virtual space. So you need to be aware of two things now instead of one. And also, reviews have shown that the effects are small, sometimes negative, so the picture is not so clear-cut. With Gen AI, there are possible positive impacts that has been shown on learning performance, so you learn quicker. Learning perception, the students say that they like it more this way, and some higher order thinking. And why I say possible positive impacts is that this study particularly has also been heavily criticized for their methodology. And also what we see in the literature is that what emerges many times is this illusion of understanding. So yes, the students feel that they have learned the topic, the teachers feel that yes, the students seem to have learned the topic, but as soon as the AI companion kind of disappears for whatever reason, the learning actually, like the knowledge disappears as well. So it was an illusion all the time. And also we see this over-reliance, which is that you tend to trust the large language model more and your own critical thinking less, even though we know that it's not a knowledge machine, it's not a repository of facts, it's like this statistical machine. And this less diverse set of outcomes for the same task. So different students now produce more similar output because they're using the same underlying AI system, or from different cultures, as we saw from the previous lecture as well. It may overrepresent, I don't know, United States, even though you're from Estonia and you want the Estonian version of the answer. So it's a paradox, because generative AI has been promised to be this tool for personalized education, but paradoxically it's being less personalized and more kind of converging into same. And we also in the article mentioned some possible fixes here. One is that you could try cognitive forcing functions. So you make you give more friction into the process of interacting with LLM. For example, you first wait and think with your own head, and then you ask the LLM. You get the answer on demand, not automatically, or you compare your own answer with the one that the system gives you. In Estonia, there's this traffic safety slogan, peatu, vaata, veendu, stop, look, and be certain before you step on the road. I hope to kind of hijack this with AI as well, that before you go to the answer, you first wait and think in your own head, then look at the answer and then see if it differs, why does it differ, which answer is then correct. But the problem here is that with these cognitive forcing functions, it has more friction, which means that the user might actually not use it. They're always going to look for the shortcut. So, but there are studies that claim that Gen AI can be beneficial in education, secondary education. And then we jump into the other topic, which is that, well, but the studies themselves have poor methodology. One of the problems is that the terms themselves have very vague meaning. So for virtual reality, up until this year, maybe in the next 10 years, virtual reality can mean pretty much anything when you look at the scientific literature. It's either 3D, 2D content on a computer screen, or this fully 3D immersive head-mounted displays. You don't know which is which until you go really deep into the methodology section, like what headset was actually being used, and then you realize no headset was used because it was a Nintendo Wii that they used. So it makes it hard to have like these meta reviews that claim some effect, because underlying technology is actually way different. And for AI, it's the same. It could be like from some well-known machine learning approach to some large LLM approach. You might not get it from the title or the abstract alone. And also extreme pace of progress. Things change in this field currently very rapidly, which means that some of the authors have said that like empirical studies might actually have like an expiry date. So you publish something, but it's only true for a year or so, and then you have to redo it because now like the tools have changed so much. One fix that's been proposed is this AI literacy. So obviously just people need to be more aware of what AI is. But there, the problem is that how do you measure it? When you look at the literature at the moment, there have been a few performance-based measurements, scales, and a lot of self-report measures. And the difference there is that performance-based actually like gives you a question you need to answer, like what do you actually know about this thing? It's a test. While the self-report is that you kind of guess from your own mind that how well do you know AI, you put like 7, I know everything. While if you would do the performance-based, you would get score a 2 or something. So do people really know what they're actually interacting with, and do students know what they're using? Another important point is that there seems to be a huge placebo effect, both with virtual reality and with 4 minutes? With virtual reality and with AI as well. So in an experiment, people might not be using AI, or AI might not be around anywhere, but it will be in the like a story that's being told to the users that you are now doing this study, AI is somehow helping you here, and people do actually better because they believe that there's some magical AI working in the background, while there's actually not. So this is the placebo effect. Which makes it very hard to distinguish what actually is the effect of AI and the effect of just introducing some technology. So we call for like more rigorous research on that, and we also call for more focus on other aspects that are being currently overlooked in educational settings, such as mental health, classroom practices, the role of the teacher. Currently it's very hazy, like what's going to happen, even in September, in a few weeks in Estonia. Like when we talk about these topics. Also, it's very hard to now study these changes that will happen in education because many things will happen at the same time. So new tool, different homeworks probably, huge attention from the media, huge attention from the research community. This all kind of changes the picture. And finally, we claim that the costs are underestimated. We know this from VR. You can have even either high quality experiences or very low cost experiences, but you can't have both at the same time. And it seems to be true with Gen AI as well. So you can have a free tier product, but it's very rate limited. You can have 10 questions and then come back tomorrow, or it could be very costly, but then can you afford it in like a mass scale? And yes, you can talk about efficiency, but efficiency leads to rebounds. So yes, the inference cost goes down, but then again, the model capacities go up. So now you can generate text, but also it provides you with a video and maybe like a audio version of whatever you just typed as well. So actually the costs go up and up. Also, in VR at least, there's very little curriculum-aligned content. So yes, you can have a zombie shooter and it's somehow being presented as an educational content, maybe, but so far not very good outlooks there. With Gen AI, there are many, many applications at the moment, and it's hard to know what's running in the background in all of these, and it's hard to know which one of these will survive in a year or so, because there are many startups. They might claim a lot of revenue, but they might not claim a lot of profit. So these models are very expensive to run, or the API is very expensive to use. So maybe the way to go is this pay-per-use platforms. So really, you pay by single kind of interaction, not just buying a seat and then hoping that people will use it. Or you run smaller open source models locally. It might be more costly in the beginning, but then again, secondary school doesn't really need maybe these very high-end GPT-5 capabilities. It's just very simple tasks that the students might do. So maybe it can run in the basement of the school. Maybe. And in the end, a few minutes, we also suggest to look at AI literacy and AI competency. Literacy is what you know about AI. Competency is what you can do with AI. And currently, they are intermixed, but they should be separated. And maybe we want to focus more on competency and not so much on literacy, at least in the secondary education. We need to teach prompt engineering, critical thinking, and a broader culture of AI. So thinking about how AI will affect us anyway, whether we like it or not. My co-author Jaan Aru likes to say that GPTs are genius personal trainers, so they will do, they help you to guide you, but they will not do the heavy lifting. At least we should think it in those terms. So let's not offload our thinking to these machines. Also, we need to look more at the social cultural perspectives and human factors and large-scale practical and longitudinal studies, which are currently absolutely lacking. We should do them in schools, and we have the chance now, not in the labs where it's very artificial. Of course, and there are these initiatives to do a better educational instruction set, such as now both ChatGPT and Gemini have these study modes that will not give you the answer, but try to guide you towards the answer. But let's see what happens there, and will students actually use it? Because it's for many, it's very annoying. They want the answer, they can't get the answer. They have to find the answer themselves. Quickly concluding is that move slowly rather than hastily, because there are many lessons to be learned from the VR revolution. It had all the hype, it had all the money, it never made it to this revolution. The large-scale uptake might not happen. It's a possibility. But it's very seldomly discussed in the literature, which might give this false picture and lead to another AI winter, because the hype is so high, and we are trying to make it a bit lower, saying that, look, it can go still either way. Then if it does go the kind of niche application way, then kind of we knew it before already. And focus on effectiveness, not efficiency, because learning needs to be effective and deep, not just kind of quick. So the last quote is that computer programs can scale up very well, and AI can easily scale up bad pedagogical issues and ideas. So we need to be certain that these models, these AI tutors, are actually good ones. And a bunch of references for you to see, and that's it.
Thank you. Regardless of whichever model will be used for education purposes, hide the answer from you and guide slowly to the answer. Kids will always have alternative phone or alternative app that is free of these limitations.
Yes.
So I think the big elephant in the room is Gen AI is here anyway,
yes.
Right? So we have to kind of cope, but we don't know how to cope.
Yes.
What's your take?
And now we're also providing like this governmentally kind of certified tool as well. So if previously like many students were hesitant,
is the decision made? What is the tool now? Can you?
I don't think they still know really, but it's 2 weeks still to go, so no worries. So I think that the finalizing has not been done yet, so I don't know. But yeah, that's why I like the AI Leap, is that it forces us to deal with this topic that's anyway here. And why I don't like the AI Leap is that it's moving so quickly, and we're not really sure what we're doing. But at least we try, and that's why the first year is called the pilot year now. So maybe in a year we already know that that didn't really work out, and the students will be more wise as well to know that where it is useful and where it is not useful, where it can actually backfire, and so on.
So your message to current PhD students or students who did not use that, you say that there is nothing to be afraid of because next generation will be stupider than you are or smarter than you are. What is your message?
Another good quote was that we should be aiming for this appropriate reliance on AI, not over-reliance and not like complete ban, but just appropriate reliance. And I guess that's what's in the next session, or was it tomorrow, where the students are saying, like in research, where is the appropriate uses and where are the inappropriate uses. So I think the next generation would know better when to use it.
I see the healthy skepticism in the researcher, and applause.
Thank you.
Thank you. Jan Martin Tamm.
Hey. So, hello. My topic is semantic IDs for multi-interest recommendations. The question is, what does it even mean? I think most of you don't understand some of it. I hope you understand the word recommendations, because probably most of you uses some kind of service to listen to music. So let's start with a little interactive session. Who uses Spotify or something like Spotify? Okay, I guess most of the room. Who uses Apple Music? 1, 2 persons. 3, 4. Who uses Amazon? Oh, even 4, also 4 people. So Spotify is the most popular here. So let's stick with Spotify. It is quite hard to pick the topic for this talk because we have different backgrounds, different research directions. So with this talk, I wanted to discuss some problems that I'm interested in and that might give you some ideas that you could adopt to your ideas or that could lead you somewhere. So we can start off by imagining your Spotify, Apple, or Amazon profile. What is the music that you listen to? My music is quite diverse. I can listen to this or to that, and it doesn't mean that they intersect in any way. So we can establish pretty much that users do have quite diverse tastes, and this taste might be separate. And this poses a little bit of a problem, because try to imagine your profile as one song. Can one song represent what do you like to listen to? I think not much, because it is weird. Why do I talk about imagining only one song? Because in recommendation systems, usually we represent user as one embedding per user in the latent space of items. It means that user is basically an average of the songs that the user listens to. And this poses a problem when the interests are diverse, and most of the time they are diverse. So this could lead to some potential problems. Like if we try to average it directly, if you like metal music and you like classic music, does it mean that you like symphonic metal? Probably not. But still, we all use these services, and this does not happen in reality. So what is the issue here? How does it work? Well, the essence is that we do not use like a simple one dimension to describe interest. When we use embeddings, we use many dimensions, 700, 1000, 200, 2004, so on. It can be quite a lot. And so the hypothesis is that we can pack all of your interest into this vast space of latent dimensions and somehow represent all of your interest so that all of your items can be put together to you as one item in this latent space. But this poses some problems. It makes this space more sparse. It makes it harder to train the model. It makes it harder to find nearest neighbors to give you a recommendation. And so it poses some problems. But still, it works quite decently because we live in this world, and it works somehow. But are there some limitations that cannot be overcome by this just adding more dimensions? And it turns out that it is this way, that it is possible if you are diverging from the global trend of the population, if your interests are not super mainstream, then for you, there exists no way to represent you with one vector to include all of your interest and recommendation. And moreover, not that it is only theoretically possible, it actually happens in real life and real data sets, and this was tested in the paper that I'm referring to here. So, if we want to improve this and capture more of your interest with a recommendation system, what can we do? Well, one way to do this is to adopt diversification. And, well, it works. You get all these playlists of the day that take different bands, they mesh them together, you get 5 of them, and you can listen to diverse music. But this heavily relies on heuristics, it heavily relies on predefined genres. And genre itself is a very noisy data because people by themselves cannot understand, like, is this true metal or not? Is this or that? How can you classify this? These tags are very diverse. They refer to different things. They are perceived differently by different people. And so this is a way to solve the problem. You can just take different genres and put them in one recommendation or make multiple recommendations. But this relies on human input of this data. And as we've learned from the beta lesson, that usually is better to solve problems with data than with heuristics that you input into your system. And so what would be the alternative way? The alternative way would be to get more than one vector per user to represent interests separately. And so this is what I referred to when I was saying multi-interest. It is the idea that the user can have more than one vector to represent interests that probably do not intersect with each other, or maybe they do. And so what it is in the essence, it is some kind of clustering, right? Because when we talk about interests, we talk about items that are similar to each other and they can be separated from the rest of your taste. And so one way to do it is just to do clustering on collaborative data. So what is this ones and zeros? This is an interaction matrix of users as rows listening to items in columns. So the first row, first column is the user number 1 listen to the first item. Row number 1, column number 2, user number 1 listen to the second item, and so on. We can either purely train a nearest neighbor model on this data with zeros and ones, but it is very sparse. It is usually not a good idea to do so. But still, you can do this, or you can train any model, and you would get embeddings that have some collaborative meaning that embeds this information into them, and you can then use them to get clusters. Hopefully, they will be representing similar items, and you can say, okay, I will look at your profile, see where your interest lands, and I will give you recommendations from those interests. But somehow, it feels a bit lacking because, well, clustering is not perfect, and we do not input any information about what is actually similar. So how can we input this actually similar into the clustering? How can we input the semantics? So the difference between these two, you would ask, what is the difference? And I would say the difference is that The second clusters are colored, and the first ones are not. By this, I try to represent that we actually use some different input of information to infer meaning, and this is the content information. So the information on the left is collaborative. It's only this user interacted with this item. We don't know anything about the item. But if we have a model that tries to predict the genre of a song, the tempo, tries to generate music, it understands some of the music, or video, or any object that you want to recommend. And so it has semantic meaning, this semantic closeness built into the model, into the embedding that it produces. And therefore, if we would cluster items in content space and not in collaborative space, then hopefully we would get better results. And so how can we test this? So I trained a simple recommendation model, and I clustered items in two ways. Semantic clusters is I clustered them with the model that I will explain a bit later in content space, and k-means clusters is I just use the embeddings from the collaborative space. Then I looked at users' profiles, picked the biggest of interest, and for each interest I recommended some items. And then I put them in one recommendation list, and these were the results. We can see that semantic clusters do work a bit better than the k-means clusters in collaborative space. And so this gives us hope that this hypothesis and this hunch actually has something to it, that it makes sense to cluster your items in different space, in content space that has information about the item and not only information about the relationships between items and users. And so how could this how could we adopt this, and how, well, we can just cluster items, but can we go deeper? And so trying to explain the second part of the title, the semantic IDs. So what could that be? Simply saying it is just a sequence of numbers which represent categories, semantically meaningful categories that are hierarchical. So what does that mean? So in this example, we have a semantic ID of length 3, of depth 3. And so each position refers to some codebook. And so the first one is the general representation of the items, a coarse-grained description. And so code word 2 means that it's the second cluster in this level. And the 15 means that first we go to the second cluster on the first level, and then we go to the 15th cluster on the second level. So this is hierarchical, and this second code book is actually shared between all of the clusters on the first level. So you could just train normal hierarchical clustering, but then you would have this multiplication of k times k times k, different variations of cluster centers of centroids. But this way, because the code books are shared, you actually don't have this, and you have a summation of the number of the centroids. So it's k plus k plus k. And so if we compare them of how it looks like with normal system, your normal machine learning system, you would have something like ID2, and you have no idea what does 2 means, because it's just an enumeration of an item. You have no idea, is it similar to 3 or not? You just say, I project it into some space, and then the latent space will carry the meaning. But when you look at semantic ID, you can say that, oh, so on the top level it's 2, and if the other item has 2 as the first coordinate, it means that it shares this category and it's similar. And the more categories the items share between each other, the more similar they are. And to get the full embedding of the item, you just sum the embeddings of each of these categories because of this hierarchical structure. And so how can this look in real life? This is from the paper that trained this thing on YouTube videos. And you can see that all these videos have the same prefix, the same first category, and then the same first and second categories. And so on the top level, we have some videos about food vlogs. And on the second layer, we have subcategories of this thing. So we didn't actually input any information that this category should be about food, but when we look at the data and we see what has been clustered together, we can actually see that it carries some meaning that we can understand. And what it gives us is it allows us to get more rare items that get less used, that are less popular, but still share this semantic information with the interest that you share. And I believe, because this was the paper from the guys from Google, that it probably should be working somehow at YouTube right now. And so, let's go to the scary slide and talk a bit about how it actually might work. So, as I said, you can just cluster items and you would have one level, but what if you want to have this hierarchy? So, RQV, what is this? So this is residual vector quantization autoencoder. And so we have X as an input of your pre-trained content model that carries the meaning. And we want to train an autoencoder to restore this somehow, and this would be the X hat on the right side. And so you project this input vector into some small latent space, probably of dimension 32 or so, to apply your clustering. That would be, for example, the representation Z. And then you input this vector into the first codebook, the first level. So what codebook is just a collection of centroids that represent different clusters. And you take this input vector and you look for the closest centroid and apply this code word as the coordinate for this item. So in the example above, I said that, okay, this vector has the first coordinate as 1. And so we take the C1, the first code word from the first codebook, and we calculate the residual. What residual is just a difference between the input vector and the vector that we chose. And why we do this is because we do the hierarchical clusterization, and so each next codebook and code word will be an approximation to the one that was before. And so if on the first level we dealt with color and we took some kind of blue, now we have almost white and with a star, and we look what is closest to this vector, and this would be not the heart but the star. So we take the second code word from the second code book, we calculate the residual, and so on. This level can be arbitrarily long, but usually you wouldn't have it more than 7 or 10 probably, maybe even as low as 3. And then you have your output vector as a summation of your code words, and you restore it back and you train this autoencoder, try to restore the original input. So this is how you can do it. And now come into stuff that, well, I try to do, and what interests me is that how can you apply this into the recommendation system? Usually people nowadays, they just train a transformer that tries to predict these tokens and learn these embeddings. But I was interested in how I can input this into a simpler model. And so the example of this model can be ELSA, and X here is this user item interactions, the matrix that you can see below. A is the matrix of item embeddings that we want to learn, and I is the identity matrix to make the model actually work. And so we could cluster items with this algorithm that I just described, and then apply this model to just different sections of items, different sub-matrices of this matrix. But still, it has some problems, and I don't know how to solve them yet. So if you have any ideas, you can just write me, and we can discuss this. Because, well, I would be happy to hear your input. And so, coming to an end, what are the takeaways that I wanted you to get from this talk? Is this, first, you are not limited to having only one vector to represent your entity, your user, or whatever. It may be beneficial to have more than one vector per user. And you can do this, and sometimes it gives you improvement. Second, when you cluster your items to try to get the meaning of this thing, it may be beneficial to cluster it in totally different latent space, using totally different model that uses different input, because it gets more information into your model, and even this information is as compressed as just an ID of the category. it already helps your model to do something. And third is that you can use this residual quantization to train these semantic IDs that would be hierarchical. And also, the last thing, since I have the stage here, is that this autumn, we have a special course in machine learning, and we will be discussing recommender systems. So if you're interested in this, you are welcome to join. We'll be reading papers and discussing them together. So please join. And with this, I'm finished. Thank you.
Thank you. Questions? That's why we save these about 3 to 5 minutes at the end of the presentation for questions. Maybe you should have a special course on asking questions.
Thank you for your flash talk. I actually had a question regarding one of your slides. It was the one that had the 2 different types of clusterings. If we could just look at the slide. Yeah, that one. So my question was that before you mentioned that users should have different types of clusters, but from this visualization, I see sort of clusters made over different users. So could you sort of elaborate on this figure again?
What do you mean made on different users?
So let's say we take a look at any clustering example here. And as you mentioned, there's rows for users, and the columns are meant for interests.
For items. So one row of this matrix would be the profile of a user. And so row number 1 is the user number 1. And then we have items of this user, and item 1 to 3 that goes to the first cluster, item 4 to 6 goes to the second, and so on. So we split your profile of a user by items. So each of these clustered matrices on the bottom has all 3 users, but it is split by items into 3 parts. Did I answer your question?
I think I had the similar problem on the poster. I have done clustering. I have actually implemented clustering methods. When you teach clustering, you show the data that clearly is clusterable. And in here, I do not see the clusters in the top representation. So maybe we have a little bit of hardship to understand how you get these 3 colors in the first place, and how the because the clustering is for the genres, or this blue, yellow, red by up front.
Oh,
somehow they are not really clusters. That is my problem, and maybe yours as well.
Well, yeah, it's just an example. So
yeah, just an example has to be handcrafted so that it represents. People understand immediately. So this is just a tiny point of
makes sense.
recommendation. Yeah. Okay, and your large-scale data, where you can test all of this, you get data from Spotify direct? No.
It's a data set based on Last.fm, with users listening to music.
So it's like a public benchmark data set where people compete. Good.
It's called Music for All.
Yeah. Good. Thank you.
Thanks.
Madar, Suleiman, please.
Hello everyone, my name is Suleiman. Yeah, it works. I'm going to present a solution of the problem, which is how to design a machine learning classifier that satisfy 2 objectives. One of the objectives is fairness, the second one is performance, but under one of the setting, which is you have in your training data noisy labels. And we are proposing a solution for this problem called graph-based fairness-aware label correction for fair classification. John worked with Carol Roy, my supervisor. So I will start with a problem that all of us we are doing since a long time, and we are teaching machine learning model also to learn it, which is the learning task. In order to learn in general, we use training data sets that has labels, and based on that, we try to predict some information which unseen before. And to do that, there was already some solutions existed presented at the first lecture, which is more data, training more, or more compute. Before 2017, transformer, and before 2008 also training deep neural networks on GPUs, people focused more on the quality of the data, your features or labels quality, plus the inductive bias of the learning algorithm. And it has been shown in some work that's focusing more on label noise is more important, since it's more harmful. So and then the other noise in your attributes, which clear why it's that, since putting noise in the features can make your machine learning model like more robust. Since label noise is affecting the result or generalization problem we have, we see that there is many reasons for that. For example, some models tend to overfit the noisy labels, and this will affect the initial task we have, which is learning. And another question is, I have lots of questions in my presentation which is already answered during the summer school. For example, I think yesterday there was answer of this question, why label noise exists. And the solution, solution for, or the why it exists for that, simply because of two reasons, like the scaling and the cost. Scaling, I mean when you have large data sets like ImageNets, and you manually need to annotate this kind of data, it's very expensive. And a solution for that is crowdsourcing, or different ways for obtaining the labels. And during the process of getting that ground truth, lots of error gonna exist at the end. This kind of error can be random mistakes, can be biased, and different issues. Focusing in this presentation when getting the ground truth is affected by kind of bias during the process, and in this case I will call it during my presentation as a label bias. So I'm focusing mainly on this case. So the strong assumption that all of us doing is using the training data sets and labels without checking robustness of our models against noisy, or if it has noise. And that assumption is very rare to exist. For example, here in this work in 2021, they identified in more than around like 10 data sets. Most of you know that data sets like ImageNet, CFAR, around 3.3% of that test data sets, they contain noise. And these data sources from different data modalities like computer vision, natural language, and audio. You can check all these kind of errors in labelerror.com. And one example for that is in 3 images. Here we can see they are labeled C#, right? And it's a mistake. So I think most of you are evaluating your maybe models on kind of data sets. They are like 10. You can check the website. Here I'm going to explain the type of label noise that are important for checking the robustness of your designed algorithm in a classification task. In this case, you need to design a way to check the robustness. For example, here some types is to inject in synthetic ways label noise on your data. In this way, you can do that injection of the label noise independent from the features, or dependent on the feature, or or dependent partially on the feature. But I want to focus on one case, which is corruption. Probability depends on both the label and one of the important feature called sensitive feature, like race, gender, and age. If you are interested in more of testing the robustness of your algorithms on real human data, annotated label noise already exists two benchmarks for CFAR dataset, CFAR 10N and CFAR 100N. You can download it easily. And another two important, quickly I'm gonna mention here, type of noise is a selective label problem. And the problem here that we cannot get some ground truth if we don't make a prior decisions, and this will affect at the end, like we are kind of not selecting in fair and random way the samples as existed in the data, and in this case it's called like unobserved, like kind of labels not existed in your data, so will affect like the randomness of checking or sampling and a sample from the population in a random way. Even in this case, this one, if it's also unobservable, but in the same time they are giving in some cases in clinical inspired like case, they are giving the unobservable like labels negative sample. In this case also it's a part of the selective label problem. Going back to the fairness in machine learning with label noise, some researchers shows that when you try to enforce some kind of fairness constraint during clearing on the data sets with noisy label can in negative way affect the accuracy of the group unaffected by the label noise. And in general, at the end, it's going to affect the whole the performance of your models. And as well, the interpretation of the fairness metrics used in this case is going to be wrong, and you cannot trust that metrics. And also, some algorithms which designed to be fair will be more biased than the one algorithm designed not without any fairness consideration in mind. So this is another issue when you don't check the label noise in your data. Here in my presentation, I'm going to focus on one of the fairness metrics called demographic parity. The reason for choosing that metric is that is one used in one of the baseline I'm check my work with. Demographic parity, usually it's satisfied when a classifier assigns positive prediction with equal probability across protected and unprotected groups. And to compute the demographic parity matrix is defined in equation number 2. Here is just simply the ratio between lowest and highest predicted prevalence. There is more than 100 definitions of fairness in machine learning, so I'm just taking one of them here. Another famous fairness metric like equal opportunity, equalized old, and so on. But this is the three important like metrics considered in the fairness in machine learning literature. Maybe you don't agree with that definition, so think about it like during the presentation about any fairness metric in your mind that's aligned with your value, for example. And here's the proposed methods proposing as a solution for the problem of fairness in machine learning under a label bias. Here is a scoring function proposed for each xi, which xi it's one instance is my data. I'm trying to rank all my instances based on this scoring function, which can be understood as a sum of three different components. The first one is a margin term, second one graph Laplacian fairness, the third one is fairness incentive. I'm going to focus more on the graph Laplacian since the beta value in this equation here it is 0.6 higher than the alpha and gamma, and this is the most difficult, but the rest term, margin term and fairness term, they are easier to understand. And at the end of ranking using this ranking function, I will have the order in descending order, which will give me the most uncertain instances via the margin term, and the weight of the via the graph Laplacian at the end the fairness gain after flipping. I'm going to explain each term. The first one is the graph Laplacian, which here to construct this graph Laplacian you need to design first your k nearest neighbor graph. K here in our experiment we decide to have it as a 10 only, and the weight which is considered as h weight in our graph KNN is defined in equation number 4, and it's just 1 over we have here this Euclidean metric, and this formula number 4 shows you that the sample in one cluster they will have a larger value of h weight, but the instances in different cluster or far from each other, they're gonna be have a small value of w, as we designed like that because 1 over. And then we consider there is a one in equation number 5. We have the definition of or one version of graph Laplacian. You can find it for the problem of semi-supervised learning. And here we consider also updating the weights in the graph Laplacian equations number 5 using the last equation wt plus 1, which is inspired by something called, if you heard, Ricci flow, which is once concept used in solving one of the most important, I think, recently problem in math, Poincare conjecture. Here's the last equation. It has a term Fej, which is a curvature. Here we think about it in a way that in each edge in our graph we should assign it a curvature, and this f is kind of a function that will give us a signal if that edge is a connection between samples in different cluster or in the same group or cluster. And the reason for that updating, it will help us to remove some information that is not necessary for giving us the ranking at the end at larger scale. I mean, when you think about it for the whole eyes samples, and for the also for each xi, when we are computing li, we will have like the sum for all neighbors, which is 10. Here is a simplified version of Foreman-Ricci curvature. Foreman-Ricci curvature is just a discrete version of Ricci curvature, and there is this is in kind of computation is better than another discrete version of Ricci curvature like Oliver one. This one I just simplified and means that there is no weights between the objective in the graph or the nodes, so I assume they have the same weight, and I enhance it by just after normalizing that version by w for giving me my final goal for ranking in faster way. And the signal that will give me by using the curvature is the sign of it. So usually this one, it gives an indication that for each edge in the graph, if, as I said, if they are from different groups, so it will be that function give me a negative sign. If they are from the same group, near each other, they should give me a positive one. And doing that in the last equation, which is a discrete version of the Ricci flow, it will enhance w for the, if you think about it like in the sign, after applying like for each edge that formula from the curvature, this will increase the weights for the edges in the same group and gonna decrease weights of the instances, the connection between weights of the edges between instances which are in different or far from each other in different cluster. Okay, after updating and doing that, we will have in graph Laplacian a few scenarios. One scenario in equation number 4 is when yi and yj, they are different, it's this between the parentheses always 1. And when they are the same, it's always 0. So we are focusing on the first scenario, which has also 2 cases. One case is when wij is small, and one case is when wij is big value. It has a big value. When it's small, it's normal. Since iij, they are different, it gives me an indication that they are from different cluster, and from definition of wij, this should be small, and this is normal. But when yi and yj, they are different, and yij is has a large value, it's a contradiction. It shouldn't be like that, because from the assumption that smaller, like similar instances near each other, they should be have the same label. And this is definition at the beginning, like when they are from different clusters, the edges, it's called intergroup edge. So this is the idea about it for ranking. This is, I'm not going to focus, it's just simple way to define a fairness term and margin term in the main scoring function. Just simple equation how to define the uncertain region, and the first one after flipping or flipping, how it will affect the fairness. The baseline I'm using is fair OPNC, which is an extension of OPNC method, which is ordering based noise correction. And after having the training corrected label in each training data sets, we are training it's a baseline method and the proposed method using light GPM models. And after that, we are testing on our test data sets. The data sets we are using, it has only 1% of positive. And we are injecting, as we said, the label noise on. We are injecting the label noise on the one group in the sensitive feature, and we are testing at the end. This is an injection here, and the result at the end we have is when we are injecting the label noise on different levels. For example, 5%, 10 injection like the noise rate, or 10 or 20. We have all the time improving result for using AUC metrics. Here we are focusing on demographic parity, and we could see on the noise rate 20, demographic parity higher is better in this equation, in this definition of this metric. We have better results than them. And here also more performance metrics, true positive rate, no true negative rate, precision, etc. They are comparable somehow, but mainly focusing on the true positive rate and false positive rates. We have better results here. And this is the main focus on the positive class, since it's just 1% of the data sets. And here the x-axis is in all the plots is a threshold. I plotted at different thresholds. Standard threshold is around 0.1 we select when making decision. So the optimal values for all the metrics we can check when around 0.1 on the x-axis. For also the same here. Here we have lots of references. I have to put all of them. Yes, and that's all. Thank you very much.
Thank you. Questions? I told you have to come up with the questions.
It's a question of a layperson. So thanks for the talk. So I think I understood correctly that you only corrected to achieve better fairness, but you did not improve the performance of the models.
Performance, it was improved in the AUC, as you could see here. AUC in general about all threshold, right? And as I mentioned at the beginning,
okay.
it's a solution for the trade-off, but it was improved the fairness. So
all right. Okay, good. But because I'm not interested in fairness,
we are interested in fairness as well.
So this could also be used to, if we have an automatic labeling procedure, and for some reason which I don't want to explain now, it is very costly, so we can't do it. But we found out that the data set that we use for training is noisy. The labels are noisy. So there's a way to improve it following some of your ideas. So
way to improve what exactly?
The performance.
The performance.
Yeah, we don't care about fairness because we don't have people. It's about cars driving in a simulator, so it has nothing to do with fairness. I was just curious.
No,
so
it has with fairness in the scoring function. It has one important. I included based on the definition of demographic parity. So I focused on that.
Yeah, but it's possible to focus simply on improving
the course,
precision recall.
Idea,
blah, blah.
I totally agree with you. If you so future, I was thinking about that. Yeah, only if you consider only the margin term and the graph Laplacian, for example, you don't want to focus on the fairness. That's right. But yeah, we assume here that even the scoring function, like it's will relabel your data. Even I didn't check if it will match exactly before injecting the noise. I didn't assume that like existed data sets, it is like correctly labeled in fair way, I think. And we try to access even in some references, they try to rewrite the history somehow. So we don't assume the given data set even is a fair one we want. And but I agree with you. If you don't want to focus on fairness, yeah, you can delete somehow. But the general problem generalization, I assume that in just generalized like words, it should be fair and no this kind of problem, which is performance included fairness.
Okay, thank you, Dietmar, for saving the day.
I'm happy, lots of questions. I hope, yeah.
Thank you for the presentation. I actually have a question regarding the same formula you provided on the slide. So the weights of alpha, beta, and gamma, how are these determined? Could you elaborate on that?
Yeah, I tried to focus more on the graph Laplacian. This is the idea. I put it by myself. I tried to focus on that since my initial work was on that. Then I decided to edit both of them in the process. But how it can be simply a hyperparameter and doing that. But from my side, I believe that in that, like updating the weight somehow, it in a natural way should give me the true connection between the sample somehow, that it's not included in the original data set before injecting the noise or after. So the structure, as we say about W, it will change the structure of your whole like manifold of your data somehow. It's based how I'm trying to update the weights. And this is way to actually, you can think about it like you need to normalize or think about the manifold in the how it should be the natural way of the manifold of your data. So that's the idea. How do I decide this is like just I wanted to focus 0.6 for beta, so I want this term to contribute more than the rest. But in general, yeah, it's a good question to try something else, but it was working with that sense is my focus, like to let this term play the main role. And I don't want to train a lot and doing that sometime by experience. Yeah, you can decide if you don't want to tune it.
Thank you again. And next is Rajesh Kalakoti.
I don't know which one. Okay, he's gonna.
Hello, everybody. My name is Rajesh Kalakoti. I'm doing my PhD in Taltek under the supervision of Professor Dr. Sven Nohm. Here is my title, Synthetic Data-Driven Explainability for Federated Learning-Based Intrusion Detection System. The motivation of the the main motivation of this work is this basically detecting the malicious network traffic. Machine learning has become ubiquitous and become successful in cybersecurity domain as well, especially in malware detection and intrusion detection problems. So intrusion detection the responsibility of intrusion detection system is identifying these malicious network traffic and giving the alerts. Though all these intrusion detection designed by machine learning or centralized intrusion detection system models. So here there is a there is a possibility that we lose the privacy of the internet and IoT and medical devices data. And then in 2016, Google come up with federated learning. So the federated learning is designed to allow the machine learning model collaboratively without losing the privacy of the participating client devices. So on the other hand, explainability. Explainability is also coined in 2016 by DARPA to make sure the transparency of the trained machine learning model. So here is the different types of the federated learning. There are three different types of the federated learning settings: horizontal federated learning, vertical federated learning, federated transfer learning. In horizontal federated learning, each client have the for training process, each client have the same type of the labels, and then training starts. In the vertical federated learning, one client might have the different labels, and another client have the different types of the labels, and the different types of the features as well. So, coming to the explainability, the responsibility of the explainability is making sure the trained model transparent and trustworthy. So, in the last 10 years, researchers have designed various types of the explainable AI methods. Like these explainable methods has been categorized in two different ways. One is you get the explainability by the model itself. On the other hand, you apply the a third-party post-hoc explainability method on the trained model. You will get the explanation for the trained model. So, these third-party explainability methods are called as a post-hoc explanation methods. So one of the problem of the post-hoc explanation methods is that these post-hoc explanation methods mainly depending on the training data to provide the explanation for the trained model. In federated learning settings, it's not possible to integrate these post-hoc explainability methods because of lack of training data on the server side. This is a problem statement. So these are two famous explainable AI methods like LIME and SHARP. Mainly, LIME is designed based on the surrogate model. Whatever the point you want to explain, you create the linear model in the vicinity of selected point, and then this linear model is used as a explanation score for the trained model. On the other hand, the SHARP is mainly depending on the game theory property. So it gives the various type of the feature attributions for the trained model. So FedXAI, it combines the federated learning and explainable AI, where the goal of the FedXAI is that getting the transparency and trustworthy of the model while preserving the privacy. That's the goal. So we combine the federated learning and explainability to make sure the trustworthy of the model. So since we don't have the since the server model doesn't access the training data, what we did is this: basically we trained the federated generative models. This federated generative model is responsible for generating the synthetic data. The synthetic data is used as the reference data, as the training data for the postdoc explainer on the server side to explain whatever the trained model. So for the classification purpose, we have used the federated deep neural network classifier. This classifier is responsible for detecting the malicious network traffic based on the various IP flow network characteristics. So here is the classical federated classification algorithm based on the fed average aggregation technique. So basically the fed average aggregation techniques, the server distributes the parameters of the initial model to the number of clients, and then these clients use these parameters, and then once these parameters are used for training on the local model itself, and then these parameters are sent back to the server, and then server responsibility is aggregating these parameters, and then finally you will get the model over the number of communication run. We have used the different types of the data sets, which are mainly depending on the network traffic statistical features, which are like NSL-KDD. These are publicly available data sets. So mainly we solved the problem of the binary classification. These network traffic features are having the various types of the attacks, but we have taken the normal traffic and attack network traffic. So for training this federated deep neural network model, we have used the non-IID situation. I hope if someone is familiar with federated learning, you must have an idea. So we have used the Dirichlet distribution to partitioning the data among the clients. So here are the results for the federated deep neural network classifier model. So on the different data sets using fed average algorithm. So here is the federated generative model algorithm. It's basically the federated generative model is designed to generate the synthetic data on the server. So we have used the different types of the generative networks like standard GAN, conditional GAN, and Wasserstein GAN, Wasserstein conditional GAN. So based on this, and then we have generated the synthetic data to evaluate this synthetic data on the server side. We have used the Wasserstein distance. Basically, Wasserstein distance is the Wasserstein distance computes between the synthetic data and real data, and then it gives the score of 0 to infinity, and then if the Wasserstein distance of distance between real and synthetic data is close to 0, then we say that synthetic data almost resembling to the real data. So we have identified this Wasserstein conditional GAN. This is the close to 0 or in a federated learning settings, this federated generative model. Once we have identified the best model of the federated generative model, and then we make sure these synthetic data is close to real data. So almost for all the features, synthetic data is close to real data. We have used the Pearson correlation. Basically, we compute the Pearson correlation of the synthetic data and real data, and then we find the difference between. And then if the difference is close to 0, then we say that for each feature, synthetic data is close to real data feature. Similarly for 2 data sets as well. And then we have also used these dimensional reductions, PCA and then and TSNE. PCA is basically linear-based dimensional reduction method, where we it reduces the multiple features to two-dimensional wise. So almost all the for all the data sets and the synthetic data is resembling to real data. So what we did basically, we have for explaining the global black box model. We take the sharp explainer. The sharp explainer computes the synthetic data-based sharp values and then real data-based sharp values, and then we find the difference between the real data-based sharp values and synthetic data-based sharp values. We finally get the difference between these two. So in order to show this difference of the synthetic data-driven explanations and real data-based explanations, we used the heat maps. So these heat maps are only for two data sets, and actually, due to the time limit, and I don't provide all the complete results. So yeah, so these synthetic data-based sharp values are almost close to the real data-based sharp values. So here are the post-hoc local explanations. So you take the single instance of the data point, and you sharp provides the explanations. So in this strip, the most of the features are resembling to the real data-based sharp explanations. And then global explanations as well. Mostly all the features are similar to each other. We have also evaluated these post-hoc local explanations, but I haven't provided any results for this, but because I realized that this is too much for the 20 minutes talk. Yeah, that's it. Thank you.
Thank you. This finished early for you, yeah?
Okay.
If there are no questions, then there are no questions.
Okay,
Thank you.
Good afternoon. My name is Martin Verrev, and I'm from Tallinn University of Technology. The topic of my talk is about semantic representations in the age of LLM. And the benefits there should be, but also challenges and opportunities. And I'm doing my PhD in this topic, and specifically working on auto-formalization of language, because I'm part of a common sense study group at Tallinn University of Technology, and we are building hybrid neurosymbolic AI system for question answering, so that it combines machine learning for textual understanding and the theorem prover to get accurate and explicit answers for the question that they pose. But again, like what the system consists of, it is the core of the system is the common sense reasoner that then that performs the inference. Then, but how to get those logical clauses? Then the key question is semantic parser and constructing this semantic parser. And as you see on the slides also that we are in Estonian University, but the topic is complex and ambiguous enough that we are working on English. And so that we use the parser to construct a common sense knowledge base, and also one of the features of the system is answer presentation, so that if we provide an question, then we don't get just not the answer, but also the reasoning chains that point to that answer. But just for the background, that some key concepts, that lot of information that we as humans use to function, it is common sense knowledge that it is facts about the world that everyone is expected to know. And it includes like objects, substances, environment, social norms. And some of it is written down, and a lot of it, but most of it is not presented in very formal database. Let's say that because we all know that the sky is blue, but where is it written down? Maybe it is in Wikipedia, maybe no, but everyone knows it. And the problem is that, okay, we have this lot of the statements and facts, but now how can we make this understandable for the computer to understand? Here you see the pyramid for machine translation that was drawn up by Bernard Vauquy already in 1968. And what it demonstrates here is the different levels or depths of language. At the bottom, I tried to see that. Okay, I better don't use the pointer. At the most obvious level, there is the morphological level. It tells about the grammar, the word structure, and so on. For instance, that if we perform morphological analysis, and in English, for instance, if we see that there is S at the end of the word, then we know that it is with great probability plural. And it gives some information, but not much. Then if we go deeper, then we already get some syntactical structure. It is word dependencies, the construction of sentences. It is this, what Stanza and those general NLP tools do. We lose some information because if we know about, for instance, verb phrase or noun phrase and how they relate to each other, we gain some more understanding, but we lose the data about morphology. And if we go deeper into this, about the meaning of the language, meaning of the words, meaning of the sentences, again, we gain some more information, but we lose some syntactic one. And but it is a good thing, and we get into this. So that semantic parsing, it is the task on converting natural language utterances, either written or spoken, to formal, machine understandable representations of their meaning. And it is this formal representation that right now I'm still talking about the symbolic part. It is not just machine understandable, but also human understandable that is important here. And just the overview of the pipeline. On the left side, we have some kind of word knowledge, some facts, although it can be structured, but in general it isn't. And what I do is we don't want to describe everything, but the concepts that relate to the question that interest us. Then through semantic parsing, we generate the meaning representations, but the meaning representation itself, they are not useful enough to perform logical inference. So that there is a step of enrichment, whether we get like link additional data sources to it or add confidences, for instance, for uncertain knowledge. And based on that, those logical forms, we can already perform automated reasoning. And this semantic parsing, the field has been active for quite a while. And it should be trivial. The answer is no, it isn't. Because the natural language, it is a very messy thing. Why? For instance, ambiguity. I saw the man on the hill with the telescope. Who had the telescope? Did I have? Did the man have? And when we parse something to syntactic trees, there is a lot of variability in this. Or then let's take two sentences as on the screen, that man opened the door or key opened the door. It is so that if we do syntactic parsing, then it is noun, verb, and then noun. And it is, and on this level they are identical, but if we go to deeper level and assign semantic roles to this, then we, in one case, we can refer to the man as an agent, having role of agent, meaning an active participant, and in other case, the example of key, it is the key is the patient or unvolitional participant of the event, and the event itself, it is opening. Or then co-reference resolution, he saw it, that who the hell is he, or what is it, and without knowing the bigger context, we don't know. Or then again, how to represent context, space, time, etc. Building the parser is hard, and again, in literature, the field of the semantic parsing has been called organized, that there is no universal representation scheme, there are no uniform metrics. Okay, you can consider like F1 score, maybe a metric, and not enough annotated data. Just to give a brief overview, and we don't have time, but just to structure and organize this landscape, it is just a selection of them. That unit of annotation, it can be a passage or a sentence. Usually they are like English-based, although universal dependencies, it is bilexical. It means that it is directly tied to syntax. And the deeper I go, like abstract meaning representation and anchored, then there is no direct relation between the input passage and the resulting representation. But for the basis of the parsing to choose the framework, then we chose abstract meaning representation due to it is widespread, it is expressive, it covered all those attributes in previous slides that we don't have time to cover. And it is widely adopted, it has a lot of benefits. It is directed acrylic graph, where the main participant for each sentence or each scene is the event that is defined by verb from prop bank. And it can be then the nodes are the concepts and the edges are relations between them. So that it can be described as a graph, it can be presented in Penman notation that is, it is Lisp-like syntax that where you can have all the nesting levels also, or it can be also for better processing. We can represent this as a collection of triplets. So that why it is good, it is manageable, it is both machine-human readable, then it has a lot of cool features built in, like question detection, number detection, for instance. Yeah. And then again, like, because it abstracts away from the syntax, then just to have the sanity check, then in parallel, Professor Tammet wrote this parser using universal dependencies. For instance, like example here that sentence cats are animals, then this is like we get a lot of syntactic information. But there, we built our own parser, and the approach was that at first we parse the passage, then we also in parallel we parse it using stanza and universal dependencies, and then apply this universal dependencies graph for sanity check. For instance, there to it can be if there were inconsistencies in graphs. Then we do some magic and transformation there, and then finally convert it to first-order logic. Just an example, simple sentence, Brutus stabs Caesar with a knife. We get initial graph. We do the classification magic there. We take the universal dependencies parse and combine it together to have logical forms. As you see, there are already now these contacts and variables and so on. But okay, this having this graph itself, then our next idea how to improve it was to extend the abstract meaning representation graph data. And it's so that there is a lot of linked information, but it is not linked there together. That sometimes those graphs were like too expressive, or they got syntax loops. We do this manual cleaning, we do labeling actions with semantic rows, we add context to numeric values, as I mentioned. Like, let's take example that John gave Mary 15. What is this 15? Then this parser graph already recognizes that 15, it is not just a number, but it is money. And then like grounding the events to Wikipedia entities, for instance, because if you speak about like United States, it can be written in several different ways to have this. Now this, and then feedback to the initial passage. You get something as an example here. Titanic sank in the Atlantic, and we already see that Titanic is ship that is referred to the entity RMS Titanic, and it is product, it is man-made. We already can infer quite a lot of data from there. That Atlantic is the Atlantic Ocean and so on. But okay, it is now all fine and dandy, but we want to take it like one step further. And here come in the LLMs. And when you think of the LLMs and using the LLMs, then in general they are generative that do pattern recognition and predict the next token. But for us it was the question that, okay, LLMs are so powerful, we have our own knowledge base, but what can we do with them and what are their capabilities. And there are different experiments that I'm going to describe that maybe do the auto formalization already, like in unified system based on the, for instance, take GPT-4, and so that we can simplify our tooling or pipeline. Then the approach that I took was to, I have a hypothesis that I'm working on that it is possible to reformulate the task in such way that we can use not those large language models, but those small, like under 10 billion parameter models, to achieve similar results that we could get from, it is from Spring to get achieve baseline benchmarks similar. And to that end, we chose different models, we chose different benchmarks, then we ran them, and these are some, for instance, this GSM 8K to understand the mathematical reasoning, folio for logic conversion, then different reasoning sets. And what I found out is from those numbers that if we look on the right at Llama 2, and that the speed and how much better all those models get in different aspects, it had been phenomenal. Like this benchmark number, they get like twice better every year, considering regardless of dimension. Then the other sad thing that I found is that there is this C benchmark like GSM 8K and not. It is so that if we provided those semantic annotations to the model, then it didn't improve performance but made it worse. Then again, that what it also described now, Gemma 3 is out, that it is that, and this it is, I think it was 8 billion parameter, that in small tasks, if we split them up, then they are quite performant. So that it is now, we have identified 3 different tasks, like text simplification, coreference resolution, and quantifier selection, so that can greatly improve our auto formalization methods. I'm 47 seconds over time, but I think we have still time for question and answers.
We have 5 minutes. Thank you. So in practice, how big is this knowledge-based part now? Are you working in some small world assumption that only part of the world, or trying to acquire almost as much as you can? What kind of scale are we talking about?
It is small. It is, we are speaking about like some thousand handcrafted rules. And
how many? 10,000?
No.
1,000?
No, some thousand.
Couple of thousand.
Yeah. It is, and the idea is to not to have like everything in this one big massive knowledge base like this tick, because then it is impossible to do search and so on. But to auto-formalize those parts that we need to solve this specific question.
But you see a path forward for scaling up?
Yeah.
What does the path look like?
The path looks like one reason that why I gave the speech also is that I started my PhD studies in 2019, and it was a time when BERT was state of
Pre-ChatGPT, yes.
Pre-ChatGPT, and up to one point we could ignore this, ignore those language models, but I think since 2 years ago or so, they have become so performant that now I'm trying to figure out this sensible way of how to have this symbolic part and connect it so that it really like improves the performance, not like if we see here this that the better the model, the less it negatively affects the result. I try to find a pointer. Let's have like this 0.7 point drop. There is also 0.13 point drop, and if we look at GPT-4o, then the drop is like less.
Okay, thank you again.